tensile stresses will develop. If falling temperature is there, then compressive stresses will develop. So when there is a restraint condition at the ends of the bar, then you will be having opposite nature of stresses that are going to develop. So because there is a restriction on the deformation like this, if there is a rise in temperature, then compressive stress will develop. If there is fall in temperature, tensile stress will develop for equilibrium. Next, the third condition is partially restrained. In that case, a portion, a gap or allowance is left for part of expansion, just like in the case of rails. So during summer, there will be an increase in temperature and the rails will expand. So for that, they will leave a gap or allowance or clearance, we can call, at the end, so that it is partially restrained. So this is the equation for the stress in that case. So, and I also explained to you about the compound bars, how the temperature stresses develop in compound bars when there is more than one bar of different material, maybe steel, copper, brass, bronze, like that. So in that case, we have to find the stresses. We should use two conditions. One is the compatibility condition. This is the compatibility condition. The second one is the equilibrium condition. According to the equilibrium condition, the forces developed in the bars, they will be equal. That means normally one bar will be subject to tensile stress, another bar will be subject to compressive stress. When the stress is multiplied by the corresponding area of the bar, you are going to get the forces that are going to develop. So they will be equal. Okay. That means forces developed in bars subject to tensile stress should be equal to force in the bars in which compressive stresses are developed. So we have done one problem on compound bars also. So taking one steel bar and two copper bars. Now we will discuss some more problems today. See this problem. This is also a compound bar problem only. Second problem. A bar of steel and a bar of copper, both of same length. So they are of same length. Have their ends firmly joined together. That means restrained ends. See here I have drawn the diagram. Steel bar, copper bar, both are of same length. Okay, but they are firmly restrained at the ends. They are fixed at the ends. That means there is no deformation that is going to take place at the ends to form a composite bar. The cross-sectional area of steel and copper bars are 1200 mm square and 1000 mm square respectively. So steel bar cross-sectional area is 1200 mm square. Copper bar cross-sectional area is 1000 mm square. Find the stresses in each bar when the temperature of the unit is raised by 100 degrees centigrade. So the entire system, entire compound bar, temperature is increased by 100 degrees centigrade. That means T is equal to 100 degrees centigrade. Find also the stresses we have to find. Find also the increase in length of the compound bar if it is 1 meter long prior heating. So the length of the bar is 1 meter here. So both the bars are of 1 meter length. They are equal. So S is equal to LC. That is the meaning. Length of steel bar is equal to length of copper bar. So we have to find the increase in length of the composite bar. That is delta L. Delta L we have to find out. Third one, what axial force must be applied to prevent this increase in length. So suppose if at all you want to prevent that increase in length or elongation of the bar, what should be the axial force that should be applied to resist that increase in length? So he has given ES value, Young's modulus of steel, 200 GPa, ES of EC, that is Young's modulus of copper EC, 112 GPa. Alpha S is the coefficient of thermal expansion for steel, 12 into 10 power minus 6 per degree centigrade. Alpha C for copper, it is 18 into 10 power minus 6 per degree centigrade. So this is the problem. There are three unknowns here. So this is the given composite bar, steel and copper bars of same length of 1 meter. Areas are different. Steel 1200 mm square area, copper rod 1000 mm square area, but lengths are same. In for first part of the problem, he has asked what are the stresses that are going to develop in each bar, stress in steel and stress in copper. Sigma S and sigma C we have to find out when this composite bar is increased, when the temperature is increased by 100 degrees centigrade. So when T is change in temperature is 100 degrees centigrade, what are the stresses in steel and copper? Sigma S and sigma C. That is first part. Second part, we have to find out the increase in length of the compound bar. That is delta L value for the entire thing we have to find out. And third one, suppose if at all you want to avoid that delta L, what should be the force that should be applied to prevent that increase in length? So three parts are there in this problem. So here we know that alpha C value is greater than alpha S value. You can see here for copper, the value of coefficient of thermal expansion is more than that for steel. So alpha C is greater than alpha S. So naturally, in the earlier problem also, I explained. So copper bar is subjected to compressive stress. Steel bar is subjected to tensile stress because it is restrained. Since it is restrained, copper ball tries to elongate more because its alpha value is more, but to have the common elongation for both the bars, it should be subjected to compressive stress. Similarly, compared to copper, steel will not elongate much, therefore it should be subjected to tensile stress. That is the idea. So that's what I have written here. So first let us use the equilibrium condition. So according to equilibrium condition, whatever force is developed in copper bar, that should be equal to force developed in steel bar. So according to that, you can see here sigma C into AC, that is the force PC. Force in the copper bar, stress into area, is equal to force in the steel bar, sigma S into AS. So please make this as AS. It is not AC, it is AS. So sigma S into AS. So substitute the value, AC value, area of copper 1000 millimeter square into sigma C is equal to, for steel it is, area is 1200 into sigma S. So you will be getting a relation like sigma C is equal to 1.2 times sigma S. So this is one equation. This is the equilibrium equation. Force developed in copper is equal to force developed in steel. One is compressive, another is tensile. Now second compatibility condition is this one. So same equation we have used in the earlier exercise problem also. So for the copper, the elongation, that is delta L, will be this. This is your delta L considering copper. This is your delta L considering steel. Yesterday I explained about that. So minus you will get, see, minus you will get if it is compression. Like that you have to remember. Plus you will be having if it is tensile. So in steel it is tensile, so you have plus term. In copper it is compression, you have minus term. So this is the delta L term for the entire system. So in this way, all the values you substitute except that sigma S and sigma C. They are unknowns. LC and LS, they are equal here. He has given 1 meter length. Prior, you can just cancel that. So LC term and LS term can be cancelled out. So remaining you can substitute. So alpha C is 18 into 10 power minus 6 into T is 100 degrees centigrade minus sigma C. LC you can cancel out, divided by EC value 112 into 10 power 3 or 1.12 into 10 power 5 MPa. So be careful when you are substituting in the formula, everything should be in Newton and mm square. Okay. So it is equal to alpha S T LS. So LS can be cancelled out because LS is equal to LC. Alpha S is 12 into 10 power minus 6. T is 100. See, I have substituted here. Plus sigma S, LS is cancelled out, divided by 2 into 10 power 5. 200 GPa means 2 into 10 power 5 MPa. So this is the equation we have got. If you simplify this equation, you will be getting two equations. Sigma C for sigma S. See, you have one equation here, another equation you have got here. substitute for sigma c as 1.2 times sigma s in this and solve. So you will get the value of sigma s. That means you are solving two simultaneous equations by putting one unknown in terms of the other and solving. Okay. So once you get sigma s, so 38.18 Newton per mm square, you can see that this is tensile. Brackets you can write, it is tensile stress. Now sigma c is 1.2 times sigma s, you will get 45.82 Newton per mm square. It is compressive. So this is tensile, this is compressive. So this is these are the values of the stresses. So first part of the problem is over. We have found out the stresses in both the bars. Now second part, what he has asked, he has asked the deformation in the bar. See here. So second one, find the stresses in each bar is over. Find also the increase in length of the compound bar if it is 1 meter long prior heating. That means suppose if the length of the two bars is 1 meter or 1000 mm, what is the corresponding value of delta L, increase in length? So here delta L can be found out either using this equation, this expression, or this expression. That's what I told. You will be getting the same value. So LC is equal to LS is equal to 1 meter. So 1 meter can be written as 1000 mm. Now I have taken here copper expression. If you are taking copper expression, this is delta L. So this is also delta L if you take steel expression. Any one of these you can use. Now I have taken here copper expression. See here, alpha C TLC minus sigma C LC by EC. This is the equation. Now you know all the values. Just you can substitute. LC value is 1 meter. Length is 1 meter given 1000 mm. Convert into mm. So alpha C is 1.8 into 10 power. Of course, you can just substitute that. I think I have written the simplified form. Once you substitute the values and simplify, you will get delta L as 1.391 mm. That means the deformation of the compound bar is 1.391. You will get the same answer if you take this expression. If you take this expression, RHS expression, in terms of steel, so by substituting for all this and simplifying, you will get the same answer. You can check it. So next, the third part, suppose if at all you want to avoid that this delta L, if at all you want to avoid this delta L, if you want to restrain this, if you want to nullify the elongation effect, delta L is equal to 1.391, you know, what should be the force that should be applied in the opposite direction? So that means P should be applied in the opposite direction to avoid that elongation of the compound bar due to heating. So what you have to do then, in that case, you have to take this as delta L. So the unknown will be P. So we know that delta L is equal to PL by AE. This formula you know already. So in this, you can take delta L as 1.391 into, see, 1000 is this. So what P is the unknown here. P is equal to this into this divided by this. So if you do that, you will get 155.68 kilonewton. Actually, whatever you get, this will be in Newton. Okay, because the values are substituted in Newton and millimeters. This, after simplifying this value for P, you will get the value in Newton divided by 1000. You will be getting P value. Okay, so in kilonewtons. So this is what the problem is. So these are all standard types of problems. So compound bar subjected to temperature stress. So I explained one problem yesterday, and today I had explained another problem. Now the next one, so this is a tapering bar. So it's an examination problem. It's a tapering bar subjected to temperature rise. See, what is the problem? A steel bar of uniformly varying diameter, as shown in the figure, is held between two unyielding supports. Unyielding means, once again, it is fixed support or restrained. Unyielding. Yielding means it will have elongation. Unyielding means there is no elongation. That is the meaning. Fixed support or restrained support at room temperature. What is the maximum stress induced in the bar if the temperature rises by 30 degrees centigrade? Take ES is equal to 2 into 10 power 5 MPa and alpha S 12 into 10 power minus 6 per degree centigrade. See here in this problem, so what you have to do is, it is a tapering bar, so that we have to use the formula of tapering bar here. So tapering bar formula, so for free expansion, we know that delta L is equal to alpha S into TL. So this is the expression for free expansion. So here he has given, I think he has given the value of delta S here. Yeah, delta S value is given here. So what happens here? Sigma max we have to find out here. So what is the maximum stress induced when the temperature rises by 30 degree centigrade? So here what you have to do is, so this here he has given this value. Actually it is missed here in this. Please take this in this problem itself. Given the elongation, sorry, one second. So here delta L, one second, you have to do like this. So for free expansion, alpha S TL is there, this is the formula. So alpha S is this 12 into 10 power minus 6 into T is the rise in temperature, which is 30, into L is the length of the bar, 500 mm. That means what we have done is, suppose if it is subjected to only temperature, this is the stress that is going to develop. So you will be getting 0.18 mm. 0.18 mm is the elongation if it is subjected to temperature stress. Now, due to the force, suppose what happens, suppose if you want to avoid that elongation, what should be the force that should be applied? So for that you have to use this formula. Delta L is equal to 4PL divided by pi into D1 D2 for a tapering bar. The diameter here is 20 mm. Diameter here is 40 mm. Okay, so that if you simplify here, then you will be getting the value of P as 45.238 kilonewton. So that is the force. Then if you want maximum stress, that force divided by area we have to take. Here area we are taking the average area. So please note that we have to take the average area. So if D1, D2, they are the diameters, your average area becomes 5 by 4 into D1 into D2. So P divided by that gives the maximum stress. So this is another problem wherein tapering section is given. Okay. Now, this is another problem in which case you have the don't worry about this. This is a complicated one. Such type of problem will not be given. So don't worry about that. This also you need not worry. Whatever I explained, those three problems, you be thorough. If you want, you can go through this. If you want to learn, I have done the steps here. How it has been done. You can just go through. Anyway, one problem I will explain. One more I will explain and I will wind up. See. Yeah, see this problem you can understand. The compound bar shown in the figure consists of three materials and supports a rigid platform weighing 80 kilonewton. So this is a compound bar with three bars, three materials. So this is one material, this is another material, this is another. He has not given the material name, but he has given the values. So length of this bar is 1000 mm, area is 600 mm square, Young's modulus is 2 into 10 power 5 MPa. That is steel. Okay, here length is 1500 mm, area is 800 mm square, Young's modulus 1.2 into 10 power 5 MPa. Next, this one length is 2000 mm, area is 1000 mm square, Young's modulus is 1 into 10 power 5 MPa. So three bars are there here, and the total weight carried by these three bars is 80 kilonewton. The question is, find the stresses developed in each bar if the platform remains horizontal even after loading. The meaning of this, this is not a temperature stress problem. It is a compound bar problem without temperature effect. He has not given any temperature effect here. So for that also we are using the same equilibrium equation as well as the compatibility equation. Here only thing is there are three bars here. So for the first bar, I will call this one first one as 1, 2, 3. Let us say that P1 is the force induced here, P2 is the force induced here, P3 is the force induced here. If you add all these three forces, that should be equal to 80. So P1 plus P2 plus 3P3 is equal to 80 kilonewton or 80 into 10 power 3 Newton. This is the equilibrium condition. Now you can replace these forces by the respective stresses. So this becomes 80,000. P1 is sigma 1 A1. So what is A1? A1 is 600 mm square. Area of the first bar is 600. So 600 into sigma 1, that is P1. P2 is 800. So area of second one is 800 millimeter square. So 800 into sigma 2 plus P3 is sigma 3 A3. A3 is 1000 here. Area of this bar is 1000. 1000 sigma 3. Now if you simplify this, if you divide and simplify, so 400 it converts to 400 is equal to divide by 200. That's 200 is common term. 3 sigma 1 plus 4 sigma 2 plus 5 sigma 3. This is what you get. So this is the equilibrium condition. Please note that there are three unknowns here. Because there are three bars, stresses in all the bars are unknowns. So sigma 1, sigma 2, sigma 3, we have to find out. So you need three equations now because there are three unknowns. From the equilibrium equation, you got this value. Now strain compatibility equation, we have to use two sets of strain compatibility equation. So what it says is the total elongation in each bar remains same. Okay, total deformation in each bar remains same means delta L1 is equal to delta L2 is equal to delta L3. That is the condition. Now that I am using here, see, first I will take delta L1 is equal to delta L2. Next I will take delta L2 is equal to delta L3. Okay, so it is separate. So two equations are written separately so that we get two equations here. And one more equation is here. So three equations totally you get. You can solve it to get the unknowns sigma 1, sigma 2, sigma 3. Now what is delta L1? Delta L1 is P1 L1 by A1 E1. So P1 by A1 is nothing but sigma 1 stress. So sigma 1 L1 by E1 is equal to, similarly, this is P2 L2 by A2 E2. So P2 by A2 is sigma 2. So sigma 2 L2 by E2. So similarly, you can write here. Now substitute the known values. L1 is the length of first bar. Length of first bar is 1000 mm. It is given here. See, 1000 mm. So L1 is 1000. E1 value Young's modulus is 2 into 10 power 5. Sigma 1 is unknown. Similarly, is equal to sigma 2 is unknown. L2 is 1500. E2 is 1.2 into 10 power 5. It is given in the problem. Next here, sigma 2 is unknown. L2 is 1500. E2 is this much. Is equal to sigma 3 is unknown. Into 2000 is length of the third bar. Divided by E value is 1 into 10 power 5. If you simplify this, this is what you will get the relation between sigma and sigma 2. This is what you will get the relation between sigma 3 and sigma 2. Now, from this, what happens? There are three equations now. From the equilibrium condition, you have one equation. From the compatibility condition, you have two equations. So, totally three equations, three unknowns. So, you can solve. What you have to do is express sigma 2 in terms of sigma 1. Express sigma 1 and sigma 3 in terms of sigma 2 and substitute here. So here sigma 2 becomes sigma 1 divided by 2.5. Here sigma 2 becomes sigma 3 divided by 0.625. So substitute for sigma 1 and sigma 3 in terms of sigma 2. Correct. So here sigma 1 is 2.5 sigma 2 that you have to put here. For sigma 1 you have to put 2.5 sigma 2. For sigma 3, you have to put 0.625 into sigma 2. So then what happens? So only one unknown will be there. That becomes sigma 2 is the only one unknown. So you see here, that has been done here. So we have expressed sigma 1 and sigma 3 in terms of sigma 2 and we have solved. So sigma 2 you are going to get 27.35 MPa. So that is the stress in the second rod. Then if you just use these two, you will get the sigma 1 and sigma 3 values. Okay, that's what is the answer. Suppose if they ask you to find the elongation of the composite bar, then you can use this condition. Delta 1, delta L1 is equal to delta L2 is equal to delta L3. All the three deformations are same. So you can use any one expression. So suppose if they ask in this problem, calculate the change in deformation, calculate the deformation of the composite bar, then you can use delta L1 is equal to P1 L1 divided by A1 E1 or sigma 1 L1 by E1. So this you can substitute. So delta L1 in this case becomes sigma 1 we have calculated here 68.375 this value into L1 is 1000 divided by E1 is 2 into 10 power 5. Just simplify that, you will be getting delta L in millimeters. Okay. Otherwise you can use this also. You will get the same answer. You should get the same answer. Otherwise some mistake may be there in the solving of equations. You have to check. Okay. So whether you find delta L1 or delta L2 or delta L3, all are equal here. That is the strain compatibility condition. So you will get the value in millimeters. So this is another problem wherein it is subject to only force. There is no temperature stress problem. So don't worry about this problem. Okay. Now lastly, I want to explain you some terms which are used in strength of materials. So already I have explained you about brittleness and ductileness of the properties. So there are some more terms which are used in explaining the properties of materials. Hardness. So first one is hardness. So what is hardness? Hardness is the ability of a material to resist inundation, indentation or surface abrasion. So if the surface is very rough or if the surface can resist the indentation, then we say that the surface is very hard. Otherwise, it will be smooth. If the surface is subjected to indentation or abrasion, then if some deformation takes place on the surface, that is, then we call it as a soft surface. So you are going to conduct a test in the BMT laboratory called hardness test. Vickers hardness test, Brinell's hardness test. So it is a measure of the surface hardness. Okay, surface hardness. Similarly, on concrete surfaces also, you might have seen they are going to conduct what is called rebound hammer test. Rebound hammer test. So they are going to punch that concrete surface with a rebound hammer. So with what force that hammer comes back. So that gives an idea about the hardness. Okay, that is one of the properties of the material. Then stiffness. Second property is stiffness. It is a property of the material by virtue of which it can resist deformation. So suppose if a material is subjected to tension or compression or bending effect also may be there. In this chapter, we are dealing only about tension, compression and shear. Okay. So we discussed about normal stresses as well as shear stresses in this chapter and their relationship. Sometimes the member may be subjected to bending effect also. It is also called as flexure effect or bending effect. So stiffness means we say that the material is stiff if it can offer resistance to any of this. It can offer resistance to elongation, it can offer resistance to contraction, or it can offer resistance to bending, or it can offer resistance to torsion. So these are all the different, or it can offer resistance to shear deformation or angular deformation. So then we say that the material is very stiff. So the measure of stiffness of the material is its modulus of elasticity. So modulus of elasticity is a measure. If the more the value of modulus of elasticity, modulus of rigidity, so its stiffness is more. So that is the meaning. Okay, so you can write that. So if the value of E or G is high for a material, we can say that that material is stiffer. Then the third property is called as toughness. See the wordings. So even though they look to be similar, so the concept is different. Meaning is different. Toughness. Toughness is the property of a material which enables it to absorb energy without fracture. So sometimes whenever you are going to apply some force on a material, so internal energy will develop within the material. That is called as your strain energy. It is called as strain energy. Okay, it has got every material has got capacity of holding some strain energy without fracture. So up to fracture, so every material can take load up to certain value. Afterward, it fails. You might have you have observed in the case of tension test subjected on a mild steel specimen. So you have initially the graph is a straight line, stress strain relation is a straight line, then it will increase up to yield, then it comes to lower yield point, then once again it increases up to ultimate point, then it comes down till it breaks. Okay, so breaking point or failure point. So up to that, till that failure of that material subjected to any test, it absorbs some energy within. So that capacity of absorption of energy is known as toughness. So more energy if it can absorb, it is more tough. That is the meaning. This property is very desirable in components subjected to cyclic or shock loading. So cyclic loading. Cyclic loading means once the load is increased, then it is reduced, then it is increased, reduced, increased. It is not applied uniformly. Load is not applied uniformly. Force is not applied uniformly. Cyclic load or shock load. Shock load means sudden load. So large amount of force acting over a small time, that is called as shock load or impact. You might have studied about impulse force or impact force. For example, earthquake force. Earthquake force is a shock load. Okay. So large force is acting over a small interval of time. A jet of water, let us say, jet of water is flowing. So that is a shock load type. So force is very high. So toughness is measured in terms of energy required per unit volume of the material. So that's what I told. Internal energy is going to develop per unit volume. Whatever energy it can store, that is a measure of toughness to cause rupture under the action of gradually increasing tensile load. So normally tensile load is taken as the reference. So when you gradually increase the tensile load, how much tensile load, how much that material can sustain within itself that energy. That is a measure of toughness. This energy includes the work done up to the elastic limit, which is small in comparison with the energy subsequently expanded. So up to elastic limit, whatever energy it can store, that is a measure of toughness. Next is strength. The strength of a material enables it to resist fracture under load. That's all. Strength means it can be anything. It can be tensile strength, it can be compressive strength, it can be shear strength, it can be strength, it can be torsional strength. So strength can be of any type. So general term is strength includes all the terms so that it can resist fracture under load. So whenever load is applied, it can take up the load at a certain stage. So that capacity is known as the strength. The load required to cause fracture divided by the area of the test specimen in terms is termed as the ultimate strength of the material expressed in the unit of stress. That's what I explained in the stress strain curve of mild steel. Ultimate strength. So this is the highest value of the stress that material can take. Resilience. Next word is resilience. The strain energy per unit volume of the material is known as resilience. So it is a measure. Strain energy. So energy is normally expressed in joules. Okay. So strain energy joule per meter cube per unit volume. Joule per meter cube is the unit of that resilience. It is also known as strain energy density. It is also called as strain energy density because it is expressed over unit volume, and it represents the ability of the material to absorb energy within elastic limits. Of course, that toughness and resilience almost they are unanimous. Ability to absorb energy. Okay, So then modulus of resilience per unit volume of material is known as the proof of resilience per unit volume of material is known as modulus of resilience. Anyway, we are not going to learn in detail about all this. So these we will be you require only in the fracture mechanics part. So which of course you are not dealing with. Only within elastic state how that material behaves that is only is important. But anyway, so whatever resilience you are going that material can sustain per unit volume, that is known as modulus of resilience. And proof resilience is nothing but it is a common term used for the maximum strain energy which can be stored in a body. So this happens when the body is stretched up to the elastic limit. At the elastic limit, whatever energy is stored at the elastic limit means after that it goes to permanent deformation, plastic state. So in the elastic state, whatever up to the highest point, elastic limit, up to the elastic limit, whatever maximum strain energy that can be stored in a body, that is known as a proof resilience. So the corresponding stress at that time is known as proof stress. So this is what I wanted to explain you in the module 1. So module 1, so in a nutshell, what are all the things we discussed in module 1? So first we discussed about the stress and strain, linear strain. Then Hooke's law, within elastic limit, stress is proportional to strain. Sigma is directly proportional to epsilon, or sigma is equal to E into epsilon, where E is the Young's modulus. So that is then what are the assumptions made in deriving those Hooke's law. So that we discussed. Then simple problems on finding the stresses and derivation on finding the elongation of a bar subjected to tensile or compressive load. So these tensile and compressive forces, they are also called as normal forces or direct forces because they act perpendicular to the cross section. Okay, so we derived some equations for deformation delta L for uniform bar. For example, PL by AE, that is explained for delta L in prismatic or uniform bar having same cross section throughout. Then we derived expressions for tapering circular bar, delta L expression for tapering circular bar, then delta L expression for tapering rectangular bar also. Then deformation due to self weight of the bar when it is hanging, when it is subject to self weight, how to compute the deformation, that also we derived. So those 4 derivations we have done. Then we discussed about stepped bars. Stepped bars means if the bars are having different cross sections, how subjected to forces at the ends, how to find the stresses and deformation in stepped bars. Then we discussed about generalized Hooke's law. Generalized Hooke's law, when there is a 3-dimensional stress system, sigma x, sigma y, sigma z, how we are going to use those stresses in finding the elongations of the strains in the 3 mutually perpendicular directions. So for that, we have to take the sum of linear strain as well as lateral strains. So in one direction, if it is tensile, in the other 2 directions, it will be compressive. That you have to keep it in mind. And tensile is taken as positive, compressive is taken as negative when you are writing that strain expression Ex, Ey, Ez. And the sum of those 3, Ex plus Ey plus Ez, that is known as the volumetric strain. Volumetric strain in rectangular block. Similarly, we got the expression for volumetric strain in circular, that is cylindrical bar and sphere also. Okay, that derivation also we have done. Then problems on generalized Hooke's law. So that means given the stresses, how to find the volumetric strain and change in volume. So that we discussed. Then after that, we discussed about the elastic constants. There are 4 elastic constants: Young's modulus, rigidity modulus, Poisson's ratio, bulk modulus of elasticity. So among them, mu does not have any unit. Poisson's ratio does not have any unit. So other 3, Young's modulus, rigidity modulus, and bulk modulus, they have the same unit, Newton per mm square. And we derived the relationship between those 4 elastic constants. So by using those we have 3 relations. By using those three relations, if you know any two elastic constants, you can find out the other two elastic constants. So we have done problems on that also. Then after that, we came to temperature stresses or thermal stresses. In that, so three conditions: free expansion, completely restrained at the ends, partially restrained. So expressions for the temperature stresses, both in the case of rising temperature as well as fall in temperature. Then we discussed problems on temperature stresses in compound bars also. Compound bars also. So there also we are using the compatibility equations. One is strain compatibility equation, another one is the equilibrium equation. So by using those two equations, we can find the stresses induced in the bars as well as the elongation of the compound bar. Then I explained you about some of the terms used in strength of materials used to define the properties of the material. So these things we have covered. Compound bars, both thermal stresses as well as only subjected to only tensile or compressive stress, the compressive force, that also we discussed. So lot of, I think I have taken some 14, 15 classes for this. So it's a very, very important chapter, module 1. So you should be thorough with stress and strain concept and all the elastic constants concept, rigidity modulus, shear modulus, bulk modulus, Young's modulus, Poisson's ratio, then what is volumetric strain, what is thermal stress, all those things, everything you should be thorough. That's why I did in detail some 14, 15. Actually, in the syllabus, it is only 12 hours. But I have taken more than 12 hours, 14, 15 hours, because I discussed a lot of problems. So what I suggest you is, whatever notes I have sent you, so work out the same problems. So check out whether the answers are correct or not in your notebook. Okay. So derivations we have to practice. There are a lot of derivations. So two questions will come in the examination. You have to answer one question, but in that one question you can have 3 or 4 sub questions, A, B, C, D, like that. They will mix the questions. That is the thing. You cannot select. You cannot select a particular topic and read. You have to be thorough with the entire chapter because they will mix the questions. So 4 questions will be mixed thoroughly from the entire module. So that is the thing. So you should be thorough. This subject is a basic subject to understand the fundamentals of the further subjects like structural analysis, design of RCC, design of steel, design of PSC. So all these subjects. You should be thorough with strength of materials. So anyway, I have sent these notes to you. Practice the same problems. For the test, I will be giving from this portion, module 1. Module 2, I will be commencing from the next class. Anyway, I am going to announce the portions for the test later. Anyway, whatever I have done up to today, that is module 1, it will be there for the test. And one more thing, just now, half an hour back, I had sent to your group mail, class group mail, that is 2019 Civil JIT, that group mail, the question papers. Earlier question papers of strength of materials of VTU, I think I have sent 18 question papers. 18 question papers I have sent. Please download it, save it in a folder. Because I will be giving assignments from those question papers only. So I will be sending you the questions maybe today or tomorrow, first assignment questions from those question papers as well as from some other books. And also I have sent a soft copy of one textbook called Mechanics of Solids. Mechanics of Solids by Bhavi Katti. So in that, some chapters are there for you. So for example, the simple stress and strain, it is there in that. You can go through that. He has worked out a lot of problems in that also. So you can refer that also for your practice. And one more book I told you, Basavarajaya and Mahadevappa. Soft copy may not be available. So, but you can try. If I don't think it is available, soft copy. So if you can have purchase or if you can have a book from the library, it is good. So that also you can study. Then R.K. Bansal book is also there. So because why I am telling Indian others is lot of numerical examples have been solved and exercise problems are given with answers. Anyway, some of my in my notes also, some of the problems I might have taken from the exercise as well as from the worked examples. Don't worry, understand the concept. Once you understand the concepts clearly, you can solve any type of problem. So you should know what data is given, what has to be found out, which formula, which method you have to adopt. So that is the main important thing. As I already told, this subject is a numerical oriented subject. Many problems, 80%, 90% numericals only will appear, derivations only will appear, definitions are very less. So you can expect up to 80% problems only. So you have to be thorough. Don't neglect the subject. That is my sincere advice. Anyway, any doubt is there, you can ask me. From the next class, I will be going for a module 2, compound stresses chapter. So for that, to understand that the first chapter is very important. That's why, anyway, next class maybe I think tomorrow, day after tomorrow, there are no classes. Let me see. Next class, be thorough with the first chapter, complete first chapter. Any doubt is there, you can ask me. Otherwise, I will take the attendance. Question papers I have sent. Please download it. Try to solve. Try to solve the questions and the problems. Derivations I have done. All the derivations I have done. But numerical problems you try to solve. That is very important. Okay, I will take the attendance. Eighteen 28. Tejas.
Present, sir.
19002. Abhishek.
Yes, sir.
003 Ajay Kumar. 003 Ajay Kumar.
Yes, sir.
006 Divyashri. Divyashri.
Present, sir.
Sir, Ajay Kumar present.
Okay.
Sir,
010
Darshan present.
Padma.
Present, sir.
ದರ್ಶನ್ ಎಲ್ಲೋಗಿದ್ಯಪ್ಪ ನೀನು ದರ್ಶನ್
ಸರ್ ಇಲ್ಲೇ ಇದ್ದೀನಿ ಸರ್.
ಕನೆಕ್ಟ್ ಆಗಿದ್ಯಾ ನೀನು ನಿನ್ ನಂಬರ್ ತೋರಿಸ್ತಾ ಇಲ್ಲ ಈಗ ತೋರಿಸ್ತಾ ಇದೆ ಅಟೆಂಡೆನ್ಸ್ಗೋಸ್ಕರ ಕ್ಲಾಸಿಗೆ ಬರೋದಲ್ಲ ಸಬ್ಜೆಕ್ಟ್ ಕಲೀಲಿಕ್ಕೆ ಕ್ಲಾಸಿಗೆ ಬರಬೇಕು ಅಟೆಂಡೆನ್ಸ್ಗೋಸ್ಕರ ಅಲ್ಲ
ಕ್ಲಾಸ್
ಕ್ಲಾಸ್ ಬೇಡವಾ ಅಟೆಂಡ್ ಆಗಿದೆಯಾ ದರ್ಶನ್ ಅಟೆಂಡ್ ಆಗಿದೆಯಾ ಕ್ಲಾಸ್ ಕೇಳ್ಕೊಂಡ್ಯಾ ಕ್ಲಾಸ್
ಆಗಿದ್ದೀನಿ ಸರ್.
ನಿನ್ ನಂಬರ್ ಡಿಸ್ಕನೆಕ್ಟ್ ಆಗಿತ್ತೇನೋ ನಿನ್ ನಂಬರ್ ಸ್ವಲ್ಪ ಹೊತ್ತು
ಇವಾಗ ಡಿಸ್ಕನೆಕ್ಟ್ ಆಗಿತ್ತು.
ಓಕೆ ಸೊ 010 ಪದ್ಮ
Present, sir.
11 ಪ್ರೀತಿ
Present, sir.
then 12 ರಾಹುಲ್
Present, sir.
13 ಮೇಧೇಶ್
Present, sir.
14 ಸಾಯಿ ರಾಜಾರಾಮ್ 14 is there?
Yes, sir.
16 Sri Lakshmi.
Present, sir.
17 Shreyas.
Present, sir.
18
Present,
is also
sir.
Shreyas. Okay. Ibru Shreyas idira ನೀವು?
Yes, sir.
Yes, sir.
Okay. Shweta 19.
Present,
19. Then 21 Surya.
Yes, sir.
Okay, good. 15 students. Okay, so work out the problems, whatever I have explained in the class. So
Yes,
have a
sir.
notes of your own. Yes, any doubt?
No, sir.
No doubt. Okay. For the first test, you should be thorough with all this up to today's content. Okay.
Yes, sir.
Thank you. Thank you. Download the question papers and save it.
Thank you, sir.
Okay, thank you.
Thank you, sir.